In this clip, we'll cover one of the simplest and lowest cost sensing devices, the thermistor. As indicated by its name, the thermistor has resistance, which is dependent on the local thermal conditions, that is, temperature. Here we see an image of a low-cost thermistor, along with its electrical symbol. As indicated in the symbol, the resistance is variable. Most low-cost thermistors have resistance that is inversely proportional to the temperature. These are referred to as NTC, or negative thermal coefficient devices, in which the change in resistance over the change in temperature is a negative value. Thermistors are specified by a few parameters. First is the nominal resistance, that is, the resistance at room temperature, or 25 degrees Celsius. The resistance depends on the device, but 10 kiloohms devices are very common and typically low in cost. The second parameter is operational range. Minus 50C to plus 130C is not uncommon, so certainly for nominal living conditions, for example monitoring room temperatures, these devices will survive. The final parameter is the thermal resistivity coefficient, which depends on the particular device. A typical value is a minus 500 ohm change per degree Celsius, or about 5% per degree Celsius change. However, this coefficient comes with a caveat that we'll see clearly in the next slide. The thermal resistivity coefficient is the slope of this line, and thus a particular value is only good over a small portion of the full operational range of the thermistor. For example, this red line here, the slope of which around room temperature would be the coefficient for that particular operational range. As you can see from this curve, resistance versus absolute temperature is a nonlinear relationship. This nonlinearity is further noted from the equation that approximates the relationship between temperature and resistance. In this equation, A, B, and C are coefficients that are material and device dependent. So how do thermistors work? As noted, there's a negative relationship between temperature and the resistance in an NTC device. Another way of looking at this is as temperature increases, the conductivity of the device improves. This is a characteristic of the semiconductor material that is used to make the device. As the material gets warmer, more electrons make their way to the conduction band, thereby reducing resistance. These materials tend to be metal oxides that have undergone some ceramic processing. Let's look at an example circuit that we can build using a thermistor. Suppose we want to create a low temperature alarm. Let's see what we can do with a voltage divider. Suppose we have a 100 k ohm potentiometer in series with a 10 k ohm thermistor. Here's our potentiometer, and we have that in series with our thermistor. And this has value 100K, full range, and this is nominally 10K ohm. Let's set the voltage at the top node to be plus 5 volts, and the voltage at the bottom to be a negative 5 volts. And let's investigate what happens at this node here, and we'll call this voltage here V out. If we adjust the potentiometer to be of a value of 10 k ohm, then at room temperature, that is at 25C, we know that our thermistor will also have value at 10 kiloohms. And thus, the voltage V out will be halfway between the voltages at the top and the bottom of the parallel string. That is, V out should be approximately 0 volts. As the temperature drops lower, the thermistor resistance will increase, and a larger percentage of the voltage difference will occur across the thermistor. As a result, the output voltage will become positive. We can use a comparator, a device we can build with an op-amp, to let us know when this voltage is greater than 0. and then use that output to turn on an alarm. If we wanted our circuit to detect freezing, then we would need to adjust our potentiometer. By looking at this curve, we see that at freezing, the thermistor has approximately a 33 k ohm value. As such, we would set our potentiometer also to 33K, and then when the thermistor's value turned out to be greater than that, because the temperature was less than 0 Celsius, our Vout would become positive. But as long as the temperature was above 0 Celsius, the thermistor resistance would be less than the potentiometer's resistance, and the Vout would be less than 0. One could create a low temperature detector digitally as well, using a fixed resistor, say 100 k ohm resistor here, and setting the top of this series chain to 5 volts and grounding the base of the thermistor. We could then investigate, as before, what happens at the node between these two components. Let's call this thermistor resistance RT. Then Vout can be found from a voltage divider as 5 volts times RT over 100K plus RT. The output of this voltage divider can be provided to an analog to digital converter that will produce a number based on the node voltage. In the microcontroller code, you would compare this value to a number that corresponds to your temperature threshold and set an output alarm or heater accordingly. In the next clip, we will discuss another resistance-based sensor called a photoresistor, which is sensitive to light intensity.